Okay, so we're going to take a break from that slightly more theoretical perspective and actually just kind of do some stuff here. So the doing part is much easier to kind of wrap our head around. But that theoretical part of the fundamental theorem of calculus is good to know. It's good to understand that because you get a much deeper appreciation of what we're doing. But really, we just want to do it for now. Okay, we want to practice doing this. So here I want to find the area underneath the curve from 0 to 3. I've drawn the curve here from 9x minus x cubed from the area under that curve from 0 to 3. Okay, so that's going to be 0 and 3 here. So when I integrate this, I want to find the antiderivative. So I'm going to go 9x squared over 2 minus x4 over 4. And I want to take that from 0 to 3. Okay, and the area then represents, under that curve, represents the displacement on the antiderivative function. So there's my antiderivative function. I want to find the displacement on that. So I'm going to end up with 81 over 2 minus 81 over 4. So that's going to give me 81 over 4 units squared. So this area here is going to end up being about 20.25 units squared. Okay, so that, again, this is the idea of the fundamental theorem of calculus. The area under this curve is equivalent to the displacement on the antiderivative. Okay, let's try another one here. So looking at this one here, we should really sketch a graph of this. We should have an idea what this looks like. So it's going to have, if I factor the x squared out, I'm going to end up with a bounce and a 0. So it's going to be, it looks like it's going to bounce here. It's going to go bounce and then have a 0 at 2. Okay, and then we're going to integrate from 2 to 3. Some point there. Okay, so I'm going to anti-differentiate this. So I'm going to end up with x4 over 4 minus 2x cubed over 3. And we want to integrate this from, I'm just going to color code this, from the lower bound of 2, from 2 to an upper bound of 3. Okay, so there's my upper bound of 3. Okay. Write this a little bit neater here, upper bound of 3. And so we want to find out that area in between. Okay, so this shaded area here is what we're going to find, and we're going to use the displacement on the antiderivative to find it. Okay, so I'm going to plug in 3, so I'm going to end up with 81 over 4 minus, I'm going to plug in my 2, I'm going to end up with 2 times 8 is 16 over 3, and getting a common denominator and subtracting that, it's going to be 243. So 243 minus 64 is going to be, looks like 179 over 12. 179 over 12 is my area. And that's approximately equal to 14.91 or 92 units squared. Okay, so that's my area I'm going to find in there. For next one, same thing. We want to, we've got some kind of graph here like that from 0 to 3. We want to find out this area. Okay, it's an exponential graph. The derivative, the integral, or the antiderivative of an exponential is itself. So we're going to end up with 2e to the 2x. We want to divide by 2. So there's my antiderivative function. And we're going to use this displacement to calculate the area under that curve. So we'll just plug it in. So the 2's cancel out. E6 minus E0. So that's going to be E6 minus 1. Whatever that area is, I guess we can calculate that. E6 minus 1. We're getting an area of approximately 402.4 units squared. Okay, so by the time it hits 3, it's going to actually be quite high. The scaling is not, great there. Okay, so same thing here. We want to find the antiderivative function for this. Okay, we want to find the area underneath this curve, so we're going to anti-differentiate. So we're going to end up with tan, and then divide by 2 because of that extra 2 in here, right, which we have to undo with we have to undo that chain rule from 0 to 0.5. So this works out to be tan of 1 minus tan of 0. Okay, well, tan 1, I don't know what that is, but tan 0 is 0. Tan 1 on my calculator is 1.55, or round that to 1.56, minus tan of 0 is 0. So we're going to end up with an area of 1.56 units squared. Okay, that's the area underneath that graph. Okay, so that's using that second idea of fundamental theorem of calculus, that we can use the displacement on the antiderivative to find the area underneath that graph. There are some properties to the definite integral, and essentially they follow derivative properties, right? We have a constant, we don't differentiate constants, so we don't integrate constants. We differentiate f and g separately if they're separated by plus. We integrate them separately if they're separated by plus. Part 3 is essentially, property 3 essentially, if I want to integrate from a to b, I can split up this integral. I can just say, well, I can integrate from a to c, and then add it to the integral from c to b, and those two integrals, those two areas, add up to the area if I just integrate straight through. And c can be any point in between. And the last one here, the last property, is this idea that if I switch the bounds of integration, I will end up having a negative integral. Okay, so I'm going to just draw this, write this out algebraically. So basically, what this is saying, that if I say, here I have f of b, sorry, I'm going to write big F, sorry, big F of b minus big F of a. That's really what it means. Okay, and how does that compare to if I did big F of a minus big F of b? Because this is what this is saying. Okay, well, if I reverse subtraction, I just get the opposite sign. So that's what's going to happen. So if I reverse my integral, my bounds of integration, instead of going from right to left, okay, here I go left to right, I get the opposite area. Well, that seems perfectly fine. Algebraically, that works. Now, try to understand how this works in a graph as well. So let's say I have a graph. Okay, I'm just going to have just draw some random graph here. Actually, I'm going to do like that. Okay, so I'm going to start, say that I have a point A and a point B here. Okay, so this displacement is negative if I'm going from right to left. Okay, so if I go from, left to right, that displacement is negative. So imagine this being a velocity time graph. That makes perfect sense. Because if I go from this point time to this time, it looks like I've got negative velocity, so I've got negative area. Okay, but if I go in the opposite direction, if I go from and integrate from, instead of A to B, I integrate B to A, and I want to know my displacement from B to A. That's what really I'm doing. I'm asking, what's the displacement from B to A? Well, if I'm going backwards here, I'm going to gain position going this way, in this direction. So I've lost position this way, so I've gained position this way. So that's going to end up being, if I go backwards, that's going to end up being a positive area. Okay, so backwards is going to be opposite. So in this case here, I've gained position going from left to right. I would have lost position going from right to left. So everything is opposite when I go in the other direction. Okay, so we have to be careful of that. So I'll draw just another picture here, and I'm gonna do, okay, let's just do like this. And so this area, let's say I start, I'm just gonna draw a point like that. You don't have to start. We're just gonna have some arbitrary starting point A here. In this direction, this would be negative, right? Going this way. If I go in this direction here, this would also be negative. Okay, it's going to be the opposite of whichever direction I'm starting at. So when we establish functions, there's my arbitrary starting point A. If x is here, that's negative area. If x is here, that's also negative area. Okay, so we have to worry about and make sure we understand that this starts showing up when we start establishing function, the direction that we want to integrate. Usually we're going right to left, but if we want to go backwards, and that's the same issue here. If I'm going backwards from A to B, I have to remember that all my areas are going to be opposites. Okay, so those are kind of two different perspectives. One is fairly easy to understand because, yeah, if we just switch the subtraction, it's just going to be backwards or opposite. Okay, but it does manifest itself in graphs when we start looking at the graphs.